Hello, my name is Matthew Davis. I am the Research and Development Director for Luna Innovation's Lightwave Division. Welcome to our presentation on a universal, non-intrusive battery monitoring and failure prediction system, a technology that has the ability to identify and locate a failing cell within any battery before it enters a thermal runaway condition, preventing the catastrophic loss of the asset or injury to personnel. This effort has been led by Luna, partnered with Dr. David Wetz at the University of Texas in Arlington, who has been instrumental in testing and providing feedback to our team. Luna Innovations was founded in 1990 to develop and commercialize fiber optic sensing technology and went public in 2006, traded on the NASDAQ under the ticker symbol LUNA. Since our founding, we have continued to develop unique capabilities in high-performance test products that sense physical measurements such as temperature, strain, pressure, and acceleration. This technology has many applications, including telecommunications, defense, and the industrial sectors. Luna has a history of commercializing SBIR-related research by transitioning it into our own branded product lines or through the generation of licensed IP. This has led to rapid growth in both revenue and our ability to acquire technologies that are complementary to Luna's own high-resolution fiber optic systems. These include the acquisition of Micron Optics, a lead in the development of high-speed single-point sensing technologies, General Photonics, a manufacturer of optical components and measurement systems, and OptiSense, a leader in long-range distributed acoustic sensing. These acquisitions enable Luna to offer diverse portfolio of client solutions. One of these customers, Lockheed Martin, recognized Luna as an evolutionary technology supplier in 2018. Batteries are the primary energy storage system for emerging unmanned vehicles and manned shipboard high-energy pulsed power systems. The problem we were presented with in this project was to rapidly identify when a battery has an internal fault in order to prevent damage to assets and personnel. These faults can occur for a variety of reasons, including overcharging, damage and defects that result from impacts or fatigue, and from inconsistencies that are present during the manufacturing process. A fault from any of these can cause the temperature to rise uncontrollably within a battery cell in a process called thermal runaway that usually results in a chain reaction with the neighboring cells, causing fire, dangerous outgassing, damage to the asset, and possibly the loss of life. It is for this reason that the Navy is seeking an innovative approach to monitoring and identifying failures beyond currently available technology, which has minimal swap-C and can integrate into the existing damage control framework. The approach we are taking to address the Navy's need involves integrating a high spatial resolution optical fiber sensor that has the capability of simultaneously measuring the temperature of every cell body and terminal within the battery. The optical fiber itself has the advantage of being non-conductive and inherently safe in high-power systems. It has also been demonstrated to be immune to the electromagnetic fields that exist in the environment and does not suffer from signal degradation as a function of length. During the course of this effort, and through related work, the technology has been demonstrated to be compatible with multiple cell types, including cylindrical, prismatic, and pouches. To address manufacturability, sensors have been integrated into prefabricated sheets that can be placed within the battery enclosure in a manner consistent with the battery's design to monitor the desired locations. This also simplifies changing out individual modules within a battery, limiting the amount of equipment downtime. The electronics that bring data in from the sensor processes, display, stores, and converts the data to an analog or digital signal, providing independent temperature measurements of each cell with a spatial resolution as small as 0.65 millimeters. This data can then be fed to a larger data management framework. Through algorithms embedded within the system, multiple options exist to perform the monitoring function. Digital data can be provided for each cell, and analog configuration can be used to report the highest temperature within a module on one channel, and the specific cell's location on the second, paired channel, or the system can be configured to emulate a thermistor, RTD, or thermocouple and provide the signal directly to the battery management system. Through a combination of all these features, the system has great flexibility and can be adapted for all monitoring and measurement situations. The fiber-based battery fault monitoring system provides valuable warnings in advance of the complete failure of a cell or group of cells before the fault propagates into a catastrophic failure. The Navy, Department of Defense, and many civilian platforms are migrating towards systems that use large amounts of stored electrical power. Within the Department of Defense, this can be in the form of manned and unmanned vehicles, communications systems, weapon systems, aircraft systems, and other devices that use a large amount of power in a very short period of time. This technology is an ideal solution for protecting these systems by providing operators with sufficient warning to take corrective action that will prevent loss of the asset. The fiber sensing system can be integrated into the power storage system and continuously monitor for faults during the operation and identify a hotspot before it leads to a major failure. Because the system has been designed to be flexible, it can easily be adapted to the power system of choice with little modification. We also envision that both the DoD and civilian markets will adopt fiber monitoring technology during the testing and qualification of battery systems. The system has been used for destructive testing, which has enabled engineers to monitor data from cells and modules leading up to failures, then using that data to redesign aspects of their particular system to increase its overall energy storage safety. This capability has further-reaching applications such as monitoring the charging of electrical vehicle batteries, adapted for improving safety of flight for both current aircraft battery systems and future electric flight vehicles, as well as renewable energy storage systems. We are continuously looking for opportunities to advance the TRL of the technology, both for its primary application of fault monitoring aboard naval vessels and within the civilian market. The Phase 1 project demonstrated initial feasibility through testing on a variety of cell types under various test conditions. Design studies were also conducted to show that the data system could be adapted to different platforms and integrated in ways that provide end users with information they need to maintain a battery-safe operation. After TRL-3 had been reached, the Phase 2 effort had focused on miniaturizing the data system and reducing overall implementation costs. Along the way, we were able to add and test additional features to broaden the scope of the potential applications. This has brought the technology in between the TRL-5 and 6, with prototypes being demonstrated in the laboratory on representative energy storage systems. What remains is to identify a platform in which the prototype can be matured and integrated with that enables high-fidelity testing. Once completed, the technology will be well poised to transition to the Navy through a prime contractor or through a systems integrator. As part of our development process, we focused on reducing the overall risk of implementing the technology with a strategy that approached the highest technical risks first, followed by risks associated with the operation of the system for its intended use. The result is that the technology is now to a point where all of the remaining challenges can be solved through engineering. Some of the key technical risks that we solved earlier included testing on a variety of cell types under a variety of conditions. During this phase, we showed that overcharging and short circuits could be detected using the fiber sensors well before conventional protection systems detected the fault. We also developed failure prediction algorithms, such as looking at the thermal rate of change to indicate if and when a failure may occur. By concentrating on all available cell types, we were able to reduce implementation risks that are associated with the different naval platforms, which may use different battery types and configurations. All of this data helped our team gain confidence that our proprietary sensing technology was an excellent fix for solving this problem. During this period, we also developed methods and procedures of implementation for the various cell types, enabling broad applicability of the technology and demonstrated a significant reduction in swap. In addition, the modular design demonstrated that the system's form factor could be modified to adjust to any number of different platforms. We also took the opportunity to add features to the system that made it more practical for the Navy's T&E as well as operational needs. The overall result is technology that is poised to be implemented through a system integrator or prime contractor into or onto specific platforms. Once the final engineering is completed, our system will be available for testing specific to the environment that it will be used in. The key feature of the system is its high spatial density, resulting in the ability to monitor the temperature at many individual and independent points along the length of a single fiber. This places a temperature measurement on every cell body and terminal within a battery and greatly increases the probability of detecting a run-of-way event. This is something that, while possible with thermocouples, would not be probable from a safety and cost standpoint. Measuring each cell is critical since we do not know in advance where the failure may occur. We have also demonstrated during testing that the fiber sensors respond faster than the thermocouple. This means that the temperature rise will be detected in time to take corrective actions, such as shutting down power to or from that particular cell or module, preventing the thermal runaway condition. The earlier that faults can be detected, the greater chance of reducing the risk of losing the asset or injuring associated personnel. Optical fiber is an inherently safe means of measuring within a high-power environment. The fiber is manufactured from a polymer-coated silica, commonly known as glass, resulting in a non-conductive tool that can be placed in direct contact with terminals and power buses. This reduces the amount of associated electrical protection necessary for integration and also contributes to improvements in speed of detection due to the proximity of the heating event. Finally, we've designed the system to be flexible with respect to how it can be implemented into the larger framework of energy storage monitoring. As a standalone system, the individual points can be monitored for maximum temperatures and rate of change. It has the capacity of providing this data in a digital format over TCP/IP connection with a JavaScript notational formatting to management system that can implement the desired logic for monitoring and control. We have also implemented an analog configuration that supplies proportional signal of the temperature at specific user-selected points to the battery management system. This feature also includes the ability to adjust the analog signal so that it will be more like that of a thermocouple or an RTD, effectively emulating and appearing to the BMS as one of those sources, streamlining the implementation. Another advancement enables the maximum temperature within a specific region to be transmitted along with the location of that region on a separate channel. This takes full advantage of the high spatial resolution measurement on every terminal and limiting the number of analog channels necessary to achieve full monitoring and control of the battery. The first step in transitioning to the fleet would be to identify Phase 2.5 funding that enables the integration of the system into a Navy battery and its monitoring system, or to support test and evaluation independently, collecting critical data on the battery as it is being used for an extended period of time. Characterization of the operating conditions during normal loading representative of the battery being in service aboard a ship would build confidence in both the battery's ability to function correctly and the functionality of our technology integrated into a larger battery management system. It also addresses qualifications that the system would need to meet for inclusion into current or future designs. During this time, a platform for future integration would also be identified. This would guide the test requirements and provide a means for addressing platform-specific design components to be completed and requirements that need to be met, including swap constraints, data transfer, and specific tasks for the system to perform, like being a passive monitoring device or having an active role within the control loop. Once proven, a prime would have full confidence to adopt the system for inclusion into platform design and requirements. Outside of the defense industry, batteries are almost ubiquitous in modern civilization, and the development of new systems is only gaining speed. This system can provide solutions in the commercial and industrial sectors by being applicable to all levels of battery design, development, and deployment. At the cell level, the high spatial resolution provides manufacturers the ability to profile the internal temperatures for cells with new energy storage chemistries and to perform initial safety and reliability testing. As those cells are built into modules, testing along similar lines can be conducted efficiently and safely under their operational conditions. Once those modules are built into full batteries and enclosed in their packs, thermal profiles can be monitored inside of the packs to ensure that they will not overheat. An additional benefit of this technology is that we're able to perform structural characterization of the packs to evaluate how damage from an external source can affect the enclosure. Once testing is completed on a battery, the system can revert to its original purpose and monitor the asset over time to prevent a thermal runaway event and monitor the battery's health during its service life. We envision that these features make our technology vital to the automotive, marine, aviation, and space vehicle industries. Furthermore, civilian deployed systems would be extremely beneficial for scalable energy storage systems. Monitoring the battery banks that store power produced by renewable technologies, which require a high-capacity storage unit to self-regulate during times when the primary sources are not generating electricity. In both the electric vehicle and energy storage domains, our sensors and data systems enable peak charging efficiency and safety, which benefits the consumer. Luna's goal is to transition the technologies that we develop to industry. We do this through direct sales, licensing, and by working with systems integrators. In many cases, the technology that we develop can be directly ported into existing products to meet a specific need or sold as a sensor system for laboratory-based test environments. In the case of this battery monitoring system, we see the best path for transitioning the technology to be partnered with a systems integrator who is designing battery safety systems for current and next generation Navy platforms. We anticipate that part of transitioning and solidifying a partnership would be to complete a test and verify the system on a Navy battery. With the verification data, we could then determine the best partnership opportunity and work towards transitioning the technology to the fleet. We do also see several products and product enhancements that will emerge from this project in addition to transitioning to the fleet. Aspects of the analog interface have already been made available to specific customers for their test needs. We've also provided sensors based on those used during our early test phases to several customers to use with our standard data system. These have been used in battery testing and characterization, which enhances the safety and performances of our customers' products. There's also the opportunity for a lower cost application-specific data system, which has an interface designed to identify a hotspot within a battery and provide that location to a larger management system. This would be most applicable to the electric vehicle charging market as a safety feature, which would enable the charging system to shut down if it detects a battery entering a dangerous state, preventing a fire, which would result in damage to property and also potentially cost lives. In summary, Luna has developed technology that we believe will benefit the Navy, is commercially viable, and will enable the protection of systems powered by large amounts of stored energy. We're looking forward to the final development and deployment of our work, and we look forward to working with you. Thank you.